Hey everybody, Dave Lindbergh in Hong Kong with yet another episode of THD Podcast. Today, joining us from the Midwest, from Iowa, somewhere near Des Moines, I'm told, is Aaron Johnson. He's the VP of Marketing and Customer Strategy at a company called Accumold. So today, we're going to find about high precision molds. Everything in audio and hearables and wearables keeps getting smaller. So how do you inject and mold those parts? I think there was a decent history in hearing aids, but now a lot of that technology is transitioning into consumer audio. So we'll find out all about the different aspects of that business. Before we go too far, let's not forget to give a shout out to our sponsor, the ALTI, the Audio Loudspeaker Technology International. So there's a trade show coming up. They're very ambitious this year. I keep saying this week after week, but October 24th, 25th in Orlando. We encourage everybody to either join ALTI as a member, and even better, get out and get involved with that event in October. So without too much delay, let's say hello to our co-host in Japan, Simon. Got a new haircut this week.
Sure did, yeah.
So does everything sound better now, or how does that work?
It sounds the same, but it's cooled off a little bit.
Okay, great. So yeah, again, Aaron Johnson, VP of Marketing and Customer Strategy from Accumold. Thanks for joining us today, Aaron. We appreciate it.
Yeah, thanks for the invite. Appreciate it.
Okay, so yeah, I kind of gave a pretty broad preface there, but I think you guys have a large history in hearing aids and some audio devices that are already very small. And we're seeing a trend with, true wireless stereo and other products getting smaller and smaller. So there's obviously some challenges in that in terms of how do you injection mold these small precision parts. And so maybe we could start with a bit of a presentation, and you can tell us a bit of the story of Accumold and how you guys became experts in this high precision molding.
Absolutely. Here, I'll start to share my screen here as I kind of jump into the conversation. And Accumold's been around for, a little over 35 years, and began in a couple of tool makers that started the company when, that Motorola had just come out with their gray brick cell phone, kind of the representation there on the far left. And that was microelectronics in the mid 80s. It only made phone calls. You couldn't text with it. You needed two hands to use it, right? So the guys that started the company saw a need for smaller and smaller plastics, but there wasn't a molding press on the market that they felt was going to give them the right accuracy, the efficiencies, everything involved from the tool making and the processing side. So they basically quit their jobs, invented what we believe was the first true micromold injection molding machine. And really the rest is history. We spent the last 35 plus years focused on dedicated to small, high precision microplastics. And I'll define that a little bit more as we kind of go on with the conversation. But really it was the start of our journey in enabling and helping customers, what we like to say is do more in the same space or more in less. And your hearing aid example is very apropos in terms of how we help that industry and other industries miniaturize or again do more in the same space. For example, when you think about today's modern hearing aids, they do more than just amplify sound. They also have higher fidelities and are after better representation. And so that's a combination of the electronics, the acoustics, the form factors, and all that goes together. And then you have the energy storage, always chasing longer battery lives or being able to put bigger batteries in smaller spaces, right? And so all of that starts to put pressure on the form factors that typically, the housings, the connectors, and the places that just basically held it all together. So what that has done, I think, in not only the hearing industry, but a lot of consumer electronics, a lot of medical device, is it starts to put pressure on supply chain that it didn't exist before. Contract manufacturers trying to find those critical components that now are beyond their typical injection molding experience. And that's small features, fine detail, and thin wall, and all sorts of kind of push the limit form factors when it comes to molding. So what you ultimately, again, end up with is, all right, you want to do more in the same space or more and less. You're starting to push on the housings and the other pieces of that. And now it's starting to collide, and you're trying to figure out, okay, how do we put this all together? And that's really where Accumold comes into the picture. And oops, if I'm going to go went a little too far ahead. And that's really where the conversation for us starts to begin. I was at a trade show. It seemed like yesterday, but it's a couple of years ago now. And I was actually coincidentally a wearables conference that I was at, and I overheard a conversation that was happening in front of me about someone who had come up with a design. They were working with a contract manufacturer, and they were frustrated because they didn't believe they could get done what they thought they could get done. And I'm over in the kind of corner raising my hand, saying, "Oh no, come over here. Let me talk to you, because what you've said so far sounds plausible or doable." But what has happened, and when it comes to miniaturization, and you're used to a supply chain, and again, maybe that supply chain doesn't have that skill set or that experience, and they're going to tell you, no, that's not possible. Mm-hmm. Or maybe they just don't want to add in a third party kind of niche player to the equation or whatnot. And so you can hit these roadblocks when it comes to innovation. And so I've spent the last 15, 16 years at Accumold trying to tell this story about here are some capabilities, just a little bit of show and tell about what you can do with microplastics, so that your innovation isn't stifled by maybe what you don't know or aren't familiar with, or what your contract manufacturer or your own internal manufacturing might not be familiar with. And so we have this pathway to innovation, which looks sunny and bright, but you kind of keep running into these roadblocks around the corner. And micromolding is one of those things that potentially can again remove some of those challenges potentially. And so when we look at that challenge, it's kind of what I was saying before. It's like the idea of trying to get more in the same space or more and less, and over stuffing a suitcase is that's the same idea. More electronics, more functionality, higher value, all the things that innovators are trying to do in their devices, and then make them smaller on top of that. And sometimes this is how I think some of our customers feel when they're trying to approach any project and design. And so one of those components that is enabling miniaturization is micromolding. And that really kind of comes down to, well, what is it then? How do you define micromolding? There really isn't a textbook definition that says this is what it is. It is injection molding. So from a general standpoint, if you're familiar with any kind of molding, it is still an open and closed mold. You still have to be able to get the material into the cavity and all that. But when you start pushing the limits, we've kind of defined micromolding in one of three ways: micro in size. Certainly, micro in features. Sometimes you have larger parts, but micro optics for a fiber optic connector has 250 micron diameter A-sphere lenses. Very small features, could be on a slightly larger part. We've done some diagnostic cartridge work for a medical device company. Maybe it's 5-6 centimeters in length, but it has microfluidic channels that are only 100 microns wide. And so, you're combining large molding, but you have these micro features to it. And then it's micro intolerances. A lot of in fact, most of the product that we mold for our customers are critical components. And then you're dealing with sometimes just a few microns in tolerance. For example, that fiber optic connector I mentioned before, probably one of the more complex type of molding that we do with those small features. And then sometimes we're dealing with plus or minus 1 or 2 microns in positional tolerance on some of those lenses. So again, you're mixing micro size, micro features, micro tolerances. In some cases, a lot of cases, it's all three of those things. But usually there's a critical nature to the component, and you're already struggling with your supply chain. They're either telling you no, or they're struggling to produce it because it is too small. the tolerances are too tight for what they're used to doing, or the features are too small, or what have you. And so it's really when you start hitting those roadblocks when a process like micromolding really can take advantage. We've been fortunate to supply to some of the coolest companies around. I wish I could say they're definitely companies that in a lot of the spaces that you and I would know, and they're looking to figure out how to bring more value to their customers. And miniaturization, as you know, continues to be one of those drivers. And it's really kind of helped, micromolding has really helped enable that.
So maybe you're gonna get into this, but is this where it's kind of a holistic solution, where you're not only looking at the metal tool, and then maybe different materials even within that metal tool, but also like how you manage the thermal control for the flow of the resin, and then even do you spend a lot of time partnering with the resin suppliers to take things further and further in terms of what's possible?
Those are great questions. And in fact, that is a great lead into this kind of part of the conversation. People ask all the time, is there a special molding machine? Is there a special technique? What's different about micromolding? And the general answer is, I usually kind of liken it to, it's all appropriate sized. You don't want to make tiny parts on a 1,500 ton press machine, right? You got to find those balances for the number of parts, the cavitation, the accuracies, all the things that you're mixing together. So there are a lot of, good micromolding machines on the market today that can be appropriate sized. But what we've really come to find over our 35 years of experience, it's kind of like buying a Steinway piano. If you don't have the virtuoso to go with it, it's just a piece of furniture, right? So the tool making, the processing, all of that goes hand in hand, and trying to understand exactly what you were talking about, how to get the material safely, correctly to the cavity, time and time again with the same precision to have those micron tolerance outputs, and to fill the cavity the way it's supposed to. I think I have a slide here coming up that will kind of help talk about the material piece of it more specifically. But when it comes to, it is still an injection molding process, and there are still standard guidelines. And people ask all the time, well, how do I design for micromolding then? And, in a general sense, it's still the same way you would design for any injection mold. Again, you still have to have a way to open and close the mold. You still have to have a way to eject the part. You still have to have a way to get the material to the cavity. So all those pieces definitely play into it. But then you're starting to talk about, well, how small can the gate be? Or what materials and how does the material play into that equation? Some people think, well, you don't need a gate just because it's really tiny. Like the example I have on the screen here, the gate is 300 microns in diameter. It had to become a feature. And we had to figure out how to build the tools so that complete part could be made and give it the geometry that it needs. It's only 800 microns long, and yet it's got a lot of dimension to it. So those types of decisions really become very important. And I used to call it kind of conversation-based micromolding. You can't just throw it over the wall and say, here, quote this. There's a lot of back and forth design for micromolding that we talk about. Yeah.
I was going to say that some of these guidelines, they really must be shared with your customer, because they have to know how these smaller components will fit into their overall device.
Well, and
if they don't understand where you're going to go with it, then you guys can't cooperate very well.
No, that's exactly right. And that's kind of where we really say start with your ideal. I had one design engineer tell me everything that he designs is as big as his monitor. And then all of a sudden you start to you see the actual sizes, and it's only 800 microns long. Then you start having a different conversation about it. But what's so difficult about just saying here's some guidelines is the depending upon the geometry and the material selection and the tolerances, any one of those things can make or break the project's success. And so we're constantly, we're encouraging our customers, okay, start with that ideal. What do you think you need in order for your project to be successful? And then we can kind of go from there in terms of what is possible, what might be possible, or if you kind of change it. And so there's some basic guidelines, but ultimately it has to be a conversation with your, molding partner to really kind of dial that in. And, sometimes again, we're at a trade show and someone will come up and say, "Oh, that's interesting. I'm working on something." I says, "Well, let us have a look at it." And like, "Oh, we're not ready yet." And we're like, no, time out. That's exactly when we want to get involved. Before you kind of settle in on what you think you need or what you might have been told is possible, let's start with what that kind of ideal state and work our way from there before you maybe design out something that you potentially could want or need. And I think one of the things that tells the biggest picture is a case study that we did a couple of years ago to really demonstrate how the material selection and the features that you're looking for go hand in hand. We tried to put ourselves in the design engineer's shoes to say, okay, here's this geometry I want. How do I match up this with the material that I'm looking that I need? And oftentimes you're picking materials because of biocompatibility or the environment it's got to survive, or heat deflection, or strength, or flexibility, or all the above. And so you're looking at data sheets and you're trying to pick out, okay, what matches the component that I'm looking for. And you go to, like this, the amber yellow color part there on the right is an Ultem PEI material, very common. They like to use it a lot in microelectronic applications, especially fiber optic connectors, because it's got a low CTE and high heat deflection. But it also pushes like cement, and you can see the gate recommendation compared to that little tiny part there. And if you're trying to match that up as a design engineer, you might say, well, there's nothing I can do here. So you mentioned earlier about partnering with resin suppliers. That's something that we've have done for years and years and years, just because we know the relationship between the material and the feature performance is going to be so connected. In fact, some of the resin suppliers will say, go try that company in Iowa. We're not sure if this part will fill. They've been able to do some pretty cool things with our materials. And so as we built this case study, we looked at this kind of extreme thin wall study. And we sent it out to our resin suppliers like any design engineer would and said, okay, what materials do you have that you would recommend to make this part? And pretty much all of them said none. They didn't have any materials that they believed would fill this part out. A couple of them said, well, maybe mold it thicker and grind it down, or maybe stair step it down and try to be helpful and come up with some ideas. We knew they all wouldn't run. We chose kind of the 11 most common materials that we see every day. We knew they wouldn't run, but we did know a few of them would. And this is really where the conversation, where the rubber meets the road when it comes to design for micromolding.
And I think just to interject from like a very layman point of view, that previous slide was an excellent slide for people just to know what all those acronyms that plastic injection engineers like, oh, we're using PEEK, we're using POM or whatever. This is an excellent slide for people watching if they want to know what all those acronyms mean.
Just don't ask me to pronounce them. I get a couple of them. Yeah, well, last I looked, there were over 80,000 thermoplastic grades of material that you can choose from for injection molding. And, some of them are just slight variations of some of these. These are 11 of the most common that we see. And then we even had a couple of them that were filled materials. So here in this slide, you can see the, kind of the output. 4 of the materials there ran the full 42:1 aspect ratio, but then you can see the variety of responses up and down the line here. The nylon there in the middle, the 18:1, you can kind of see the glass shards. So that was a glass-filled nylon. But the LCP up at the top in the middle, that was also a 30% glass-filled material. So there are ways to get the materials that you need to the right places, but it's not a guarantee. PEEK, as we talk about that, it's not to say that 3:1 is the maximum aspect ratio when it comes to PEEK, but in this particular situation, when a customer brings us a model and they say, "Can you make this?" Our engineering team first looks, okay, is it in an injection moldable shape? Can the mold open and close with the shape? And the second question is always, well, what's the material? Because we know in our minds with our experience, it's like, okay, that material is not going to match that shape, or that material is going to match that shape. And so if we had gotten this model in and they wanted PEEK, our team would have said, yeah, no, it's not really going to be viable. If they said LCP, yep, no problem. It's one of the best materials for high aspect or thin wall applications. And so that material selection piece is so important because of all of the things that go into it. Again, if you're thinking about in the audio realm, you're dealing with what does the acoustic of that material do for the sound? If you're developing headphones or hearing aids or other things that have to work with it, you've got other properties that you're dealing with that the material bring to the table. And then you're trying to match that with the geometry. And at the micro level, that can be a complex, difficult thing to navigate sometimes. And so this slide here really kind of demonstrates, I think, the difficulty and the complexity of it, but it also demonstrates the possibilities of it. And why we like to show that don't just stop at the first no. In fact, there's a major, Fortune 50 company out there, consumer electronics. I've once heard that their rule is, as designers and engineers, is they don't take no until they know no is the answer. And so you're looking at, pushing your suppliers, pushing your supply chain, pushing your own company sometimes in order to find out, is no the answer, or is it just a different path? And then if that path then is viable, does that bring you the value, the project of the project that you're trying to get done? Does it give you the competitive advantage that you're after, or that next breakthrough, and just having to push through on that? And sometimes that's exploring, services like micro injection molding that you may or may not be familiar with.
Now, is the core of the business, is there IP related to what you guys do, or expertise, or a combination of those two?
For us, it's a combination. The original micromolding setup that we built 35 years plus ago, we're on multiple generations of that, and that's something we kind of keep close to our vest as our way of processing and building tools and molding the parts. But then it really goes hand in hand with that experience that we have. We have about, I want to say 90 or so in our engineering team, and most of those are in the tool room, and many of them have been with us for a couple decades or more. And so, we're passing that down to our next generation of tool makers. And it's really been about, for us, the experience and how to approach micromolding to get the results that our customers are after. And again, there's no textbook that just says, do this, do this, do this. It's trying to, piece together that experience. Again, there are micromolding presses on the market today that do a fine job. But we believe that it is that combination between the right size machine with the experience that goes with it. I just have a couple more slides to really kind of show some of the capabilities from an example standpoint that sometimes can spark the creativity or kind of give some perspective of things that you might be thinking about. Again, this is an internal chassis for a hearing aid. It's one of my favorite parts. And if you know anything about molding, you might recognize the complexity of something like this, with slides and core pulls coming from just about every direction. And you got these thick to thin to thick to thin transitions, which a lot of times, the rules say, always go from thick to thin and don't go back again. But sometimes the situation says, no, it would be ideal if we could. And you have to figure out how to build the tool for that. And then you also have 3 discrete inserts going on here. And so one of the probably the most overlooked opportunities when it comes to miniaturization is combination parts. Figuring out how to put 2 parts together that might have been one. And sometimes they're 2 different plastics, but maybe it doesn't really matter that they could both be the same plastic, provide you the functionality that you're looking for, and then all of a sudden you have one part. In this case, these were multiple parts that were assembled, and the customer was looking to figure out how to do more in that open cavity. Again, it was back to putting another circuit board or more electronics in there for adding more functionality to their hearing aid. And what that wheel combining the two parts together then allowed them to share wall thickness between what would have been thicker two parts stacked together. Now they're sharing one thin wall, and it gave them just that much more room on the inside in order to add that, extra component or whatever they were looking for. So that combination piece, whether it's combining parts into one part or overmolding or insert molding on other components, in order to gain this is a very complex part, but in the end, it saved them assembly and gave them more functionality. And so, it was worth the effort to figure out how to do something like this, when it came down to it. And so for us, it's just a really good example of, miniaturization. Well, okay, this is a big part. It's an inch and a half long, but yet it's got all these micro features to it and the complexity to it, and the metal overmolding that's going on there as well. And so, go ahead, Dave.
Would this also include some I've heard of in-mold laminations and stuff like that, and a lot of people doing insertion of the printed antenna on the inside walls of some of these devices? Are you able to do that at these micro scales?
Exactly. There's really two basic rules when it comes to that. You can overmold anything that you can hold it. You got to figure out a way to hold it in the mold so it stays where it needs to be. And second, it has to survive the temperatures and pressures of molding, which can be extreme. So not everything, matches that. We often get asked, hey, can you overmold electronics? Well, yes, but they won't survive, at least in a lot of cases. And so, you're figuring out those types of things. There's a process called LDS or 3D MID, which is laser selective plating. Basically, you strike the plastic with the laser. Wherever the laser hits, the plating sticks. And that's allowed, again, another complementary technology for miniaturization, for you to do SMT compatible traces on the plastic. So then all of a sudden your housing becomes your circuit board, and allows you to do things, again, that open up creativity and space and opportunity. And you just have to know that it's available. You mentioned antennas. I think most of today's cell phone antennas are built using that kind of technology, because the frame is the antenna, because they just make it out of plastic and then plate it selectively. Very cool technology.
Are those I think additive or subtractives? Sometimes they'll flood coat a metal surface and then they'll laser etch away? Or is it also, you're telling me that they'll use laser kind of activation so that the plating only bonds to the traces that you've defined?
Right.
With the
This
laser?
particular process is the second, what you just described. There's a German company called LPKF. They're the leader, as far as I'm concerned, in terms of the experience with this technology. They're a laser company, but they've developed the material additive that activates when the laser strikes the plastic, and then it only sticks on those traces. And wide variety of materials available, and it's been around for a long time. And I think companies, as they've developed more and more ways to utilize it or understand how to take advantage of it, that it's really kind of growing in popularity. We like to talk about it because it's very, very complementary to miniaturization. Automotive have been using it for a long time in big, large parts. Again, it doesn't really care about the size, but if you're looking to shrink components, figuring out how to combine things together to save on space and whatnot, that's another way to do it. So it's that combination thinking. How could I combine a few things together, maybe make one complex part, but then in the end, ultimately add that component and value to your component.
Okay.
Last slide here I have is just, basically just the kind of a few examples. That small part that's in the middle was the one I showed earlier. It's 800 microns long. The part on the right is an interesting one. It's a filter, again, for the hearing aid market. Everything that I show here, we've gotten permission to show. They're legacy parts, and the hearing aid market is They're very generous. Once it hits the market, they let us show it. And they're also very representative of a lot of the capabilities of micromolding. This is a case, again, a combination. The customer had developed their own special coating for wax mitigation and wanted to create these little filters. And we figured out a way to articulate a fabric through a multi-cavity micromold and produce these little wax guards, as they were called. We ended up making a second generation smaller version, and then we've made all plastic versions of them as well with tiny micro through holes. And so again, complex little part, but that one is dealing with like a fabric overmold. And then the parts on the left, I kind of alluded to this earlier, and is some micro optics. And the reason why I like to separate those out is because of not only these small parts with small features and tight tolerances, micro optics takes that to an extreme. You think about surface finish and material clarity, and the tolerances are even tighter than most. I usually tease that optical engineers like plus or minus zero. But we're usually able to achieve in a lot of cases, a few microns here or there, and depending upon the nature of the product. But micro optics are a growing interest because of the sensor market. And you think about wearables and other consumer electronics. I mean, there's hardly anything you can't buy today that doesn't see the world somehow. It tells you're in the room. It tells you, if you're moving or not moving, all those, even your coffee maker can say hello to you probably these days, and that all comes through micro technology and micro sensors. And so the drive to, make little tiny optics and little sensor housings, and to do that in a way that they're all surface mount compatible, that's probably one of the fastest growing trends that we see in the micro injection molding realm, because of the demand in the marketplace is just growing exponential when it comes to micro sensors.
Okay.
So in the end, to maybe end on a cliche, we it's back to that start with the ideal. It's start with what you think you need in your design, and continue to push that until you find that no is the answer. And so it just comes down to that blue sky thinking when it comes to, what is innovation? Innovation means it's something you haven't done before, and then potentially something that nobody has done before. And to try to figure out how to do that, and to decide whether or not that's your next breakthrough to, make your company successful, sometimes really requires pushing beyond the supply chain that today and exploring some potential others. Again, micromolding is just one of those things. I mentioned LDS, laser direct structuring, it's called, is another one of those things that might be of interest. But there are other technologies out there. And I think, those of you that are watching this right now, you're already in that mindset to explore new things, right? Because that's what you guys are all about, is trying to discover what's out there in the world to help us you make these breakthroughs. And so it might be something you have to encourage your colleagues with. Hey, or your purchasing team. Well, we don't have them as a supplier. We're trying to reduce our supply chain. We're not trying to add to our supply chain, right? All the sorts of pushback that you might get when you're trying to design something, and you're just figuring out how you can navigate that. And, again, something like Accumold or the micromolder can be the key to enabling some of those next generation product. And so, we see a wide variety of applications. Almost all of them are electronics. The growth in wearables and hearables and consumer electronics is kind of, again, fast paced because of the demand, consumer demand, and the functionality that people are looking. And I'd say right behind that is medical device. They often mimic and follow consumer electronics. And you think about what's on the market today for diabetics, blood glucose monitoring and insulin pumps, and the technology that's all coming on the heels of wearables and micro technology and things like micromolding. So it's for us, I love it. We enjoy it because we get to see some next generation technology as it's being developed, and be a part of that, kind of supply chain, if you will. And then speaking of supply chain, you mentioned earlier, we're in Iowa, right in the middle of the country. And I always tease, don't worry if you don't know where it's at. Most Americans don't know where it's at. Just west of Chicago, south of Minneapolis, in the heart of the Midwest. It's where the company was kind of born and raised, and where we've been for the last 30 plus years. And we like to say we're huge in micro, a little over 12,000 square feet or square meters in space. And about 350 people, all dedicated to micromolding. So it's a lot of fun. We have a great company and do a lot of exciting things.
So everything is designed and manufactured in Iowa. You don't sell the tools off to others or none of that type of business?
Yes, that's a fantastic question. No, for us, it's captive business, meaning we're a tool shop, but it's really for production, and they go hand in hand. You need to have them together to get the accuracies and the critical nature of those components. It would be very difficult to not have our tool shop and our molding shop in the same facility. Again, that's a model that is very, very common in a lot of ways for maybe traditional molding, but for us, it's all done right there in Iowa, in Ankeny, just north of Des Moines. But the beauty of micro is they ship all over the world quite easily. In fact, right. We get calls from logistic companies wanting to know if they, need to bring us semis. And it's like, no, just DHL. We got 100,000 that go in a little container. So it definitely makes it easy for logistics because we ship to Asia and Europe and all over the U.S. every day.
Is
Simon, go ahead.
The parts that you're making, are you getting down to the tolerances of CNC and EDM stuff, or does that come into the picture too?
Well, so from a tooling perspective, our tool shop uses, EDM and CNC type equipment, and we're often, looking to finesse that. So when you're building a tool, a mold for an injection mold, we sometimes will have 10 or 15 different specialists in the tool room working on one component or another. Specialists on the wire, specialists on the downsinker, specialists on, the CNC machining. In the end, they all got to fit perfectly together so that, the mold comes together, the cavity is exactly the way the customers need it, built with the right specifications for the material that we're going to process. So yeah, it's quite the orchestration of machining and the way we approach our tool building to come together to really hit those micron tolerances.
When it comes to part design, are your customers generally highly skilled in that, or do you end up having to do kind of help them through some of the part design aspects?
Yeah, so right. No, that's most of our customers have their general part design, but most of them are not experts on micro molding. And so we really go through this, what we call the design for micro molding phase. They've got, like I said, their ideal shape together. Maybe they have a lot of experience with injection molding in general, but maybe not where they can push the limits or what materials. And so there is a lot of that kind of design for micro molding conversations that happen at the front end of a project. And that's a really important point, Simon, because, it's one thing if you're R&D, you're just trying to make one thing to see if it works. Yeah, there's that level. You need that piece of it. But then you also eventually need to know, well, can you make 100 million of them at the same level? And so we like to start the conversations knowing, well, where do you ultimately think you need to go and to help you be successful, not just with one, but with 100 million, right? And so that conversation gets into quality. How are you going to measure the parts? Where are they going to be shipped? How are they going to be shipped? If you think about micro lenses going on halfway around the world, you don't want them all scratched up, bungled up in a big bulk, right? All of those little things we help our customers think through if they don't have that experience already. So there's definitely a learning curve to it. And really, I think our best product isn't really the parts themselves. That's the output of great collaboration between our company and our customers and their engineers working together to make the most robust project that they can.
Yep. And how about simulation versus experience in terms of tool design?
So, there's certainly flow analysis is been around for a long time. In fact, I just had this conversation the other day. If we relied on flow analysis to say whether or not we could make parts, we would have never been in business. It said we couldn't make parts that we've been making for 30 years. Now, that being said, it's come a long way in the last few years as they've gotten better at simulating what these materials are going to do in micro spaces. But we still will do simulations. On the larger parts, it certainly has a little bit higher accuracy for us. But even on the smaller parts, it can sometimes give us a few clues or give our customers a few clues, because sometimes knit lines and flow patterns will matter even at the micro level. And if we can help our customers say, no, if you can gate over here, then you're going to have this over there, and it's out of the functionality path that you're looking for. Again, that does come into play, but you kind of have to know what you're looking at and when it's telling you what's possible or when it's telling you it's not possible.
Yeah. So, and a lot of the design work that I deal with, people don't give any thought to things like you mentioned, gate position, especially. But I suppose in a micro part, it's a critical factor.
Well, again, sometimes we get customers that bring us a part and they haven't put it anywhere, and was like, okay, where can we gate? And they're like, oh, you still need a gate? Yeah, we still need a gate. And then it's that deciding factor. Okay, that's which surface, what's critical, and we have to sometimes be really creative about that, because you don't have a lot of surface area. So sometimes there's really few choices to even work with. So then, like the one part I showed earlier, you have to maybe make it a feature that you can work with in order to, kind of combine, what it physically needs to be molded, but also physically needs to be a functional part for you.
In those list of materials, I saw a suspiciously absent ABS. Do you not deal with ABS very much?
No, we do. It just didn't make that particular list. In fact, we've taken that 11 and we've run lots of other materials like ABS or PBAX or some other softer thermoplastics, TPU materials, because sometimes the customer will say, hey, I'd like to use this material. We can run it in that thin wall test mold and say, okay, it'll start to give us a clue whether or not we think it's going to work for this situation or another. So no, we do process quite a bit of ABS, just didn't happen to make that list.
Yep. And is the tool designed for one specific material, or you have a limited range you can choose?
So yes, so the shrink rate of the materials are all different. And yes, you could run any material in any mold, but it's not necessarily going to have the same, end result, because the shrink rate still, again, matters. When you think about that 800 micron long part and you have a shrink rate of 1 or 2%, well, that's a lot when you're talking under a millimeter in terms of the size. So you do have to build the tool to the material selection when you're looking for micron tolerances. If you don't have micron tolerances, that's less of an issue, but they will be different. So sometimes a customer will come to us, they don't know exactly what material they want, or they want to start with this material. So we'll have to either build the tool so we can accommodate for that, start with what we call steel safe, and then work our way from there. But sometimes that's not possible. And so we'll maybe do multiple cavities in some kind of prototype mold base in order for them to really prove out what's possible with each material they're looking for. So again, material selection is just, could not stress how important that is in the early discussions when it comes to micro parts.
And some of those parts look pretty tiny. Is there a lot of pan processing to separate the parts, or do you ship it with the sprue and everything attached?
Yeah, for the most part, no, there's no labor in secondary ops when it comes to, we want them clean out of the mold and building the mold so it'll do that. Some parts do have automation, and we'll do some sub-assembly work. We don't really consider ourselves a full contract manufacturer, though we do some light sub-assembly, and sometimes that might include a secondary op for one particular reason. But I want to say 99% of the parts come out of the mold ready to go, unless the customer has specified, no, I want it left on the runner because they need it to handle it because the part is so small. So those are done by design and do happen on occasion, just so they have some way to manipulate it themselves. Yeah.
I see. So the tool is designed that's generally broken off when the tool opens, and then it just pops the part out into a bucket, into a tray.
Right. Yeah. Either collected by robots individually, or they're popped out and drop into a tray or conveyor or bucket. Again, depending upon the nature of the part. But part handling is definitely an interesting part of micromolding when you're dealing with such small parts and small surface areas. And
you generally in a tool you're injecting multiple parts.
So yes, these days, definitely higher cavitation is of higher interest, especially in the consumer electronic space. But when you're talking about high precision components, cavity-cavity variation can be an issue. And so lower cavitation tends to be better. But it all comes down to how many parts do you need, the efficiencies and the costs that go into all of that. And so that's, again, a conversation that happens up front. Sometimes it's better to build two systems with smaller cavitations than to try to put it all into one, again, because you're dealing with all the material management and getting them to tiny spaces, at the same rate and the same levels, the same accuracies, definitely can be complex. And so for us, a large micromold would be like a 16 cavity would be high cavitation for micromolding. If you're talking about plastic spoons and you're in some 128 cavity mold that I could walk into, that's a different story. But for us, it's definitely lower cavitation, again, depending upon the need.
Do you think it's you're in sort of a protected niche, let's say, in some sense? I want to get to, do you think that the Chinese tool manufacturers have dominated so greatly because they're local to all the manufacturing?
To a certain point, but we ship to China every day. We're shipping to CMs and the manufacturing divisions of a lot of major European and U.S. customers because they don't have that level of molding, in China. And again, there's some gray area. What is exactly micromolding? And there are some fantastic molders, actually both of your next to your woods. We're familiar with a lot of really good tool makers and molders. And so, there's a certain level that the locality is beneficial, but again, because they're micro parts, logistics really is less of a challenge. And then we're dealing with the design teams that are either in California or Germany, and so they're used to just dealing with, multinational kind of setup. And so whether or not their parts are getting made in Iowa or in Asia, as long as they all come together in, the right way, that seems to be very doable.
Yeah, excellent. And in terms of quality control, how do you deal with that? Do you guys have optical measurement machines and things like that?
Yep. Of course. Most of our machines are OGP. We're doing optical and laser scanning on some of them. High power magnification, of course, to be able to measure down to a few microns. But then we also have a couple of white light interferometers that we will also use, especially on components, the optical components for surface profiles and some of those extremely small features or tight tolerances. So you have to have the right tools, of course. And then our customers also need to have some way to correlate as well. And so sometimes we'll work with them to make sure that their incoming inspection also matches. So when we know what a micron is, we all agree where it starts and where it stops. So
excellent. It's mostly going into quite high value products, is it? Your parts?
There's definitely, I would say, that's probably the higher percentage, though. Over the last 5 to 7 years or so, the demand in the consumer space for the millions of months that we have on some projects is definitely in that commodity space. But we're making that one critical component or two critical components that go together, and again, trying to find that. So there is efficiency to do it. There is a competitiveness that does make sense. But again, you're trying to look at it in the total context of your supply chain and what you need to accomplish.
So that was actually leading to my next one. You're doing parts at $1 million a month level.
In some cases, yes. It's not everything. Hearing aids aren't that high volume, but you think about sensors or some other medical components that have extreme volumes to them. Yeah.
Wow. So is that machines running? Machines running 24 hours a day, or?
Well, pretty much. I mean, we operate on a 24/7 basis, and we have over 200 presses in our facility, and the microsystems we build on demand. So if we need more, we make more. We standardize. I didn't really kind of get into the types of machines we have because we also do some what we call small molding, up to about 5 centimeters, 6 centimeters or so. And again, we usually have micro features or something to it. So we do have access to a wide variety of molding machines and capacity for high volume for sure.
And do some of these sub-assemblies, are they like plastic sub-assemblies that might go into a larger, where there's another tooling partner in Asia or in Europe somewhere, and you guys make the sweet stuff, and then you have to have an FAE in China or in Germany to help make sure it fits properly?
Yeah, almost everything we build is component level, and it's sub-assemblies. It's again, a lot of it's plastic sub-assemblies, 2 components snapped or 3 components snapped together or sonically welded. But again, we have a few other components where we're doing a few more traditional assembly, but it's still component level. We're not making finished goods where we are. We're not doing die attach and wire bonding and those types of things. And we leave that to the experts that do know that well and provide what we can to those types of assemblies.
Okay. All right. So how do people get a hold of you? Is there they find you on LinkedIn, on Twitter? What's your favorite?
No, certainly I'm on LinkedIn, but Accumold, ACCU-MOLD. For those of you with maybe an English spin, there's no U in that one. ACCU-MOLD.com. That's probably the easiest way where you can learn a little bit more about us, and check out some more examples and capabilities. And certainly there's contact details there. I'd love to hear from anybody that's interested in talking more about micro injection molding and its capabilities. We do tech days. We do a version of this presentation that goes a little bit into more in depth on who we are and what we do, and that we give to customers all over the world. Because of COVID, we started doing virtual tours. We actually have a really cool virtual tour that we do throughout our facility, and we do it live in real time, and you get to ask questions, and we try to tailor it to what you might be interested in. So we've had to be creative too when it comes to just sharing our story. So
great. Okay, so Simon, thanks as always. Aaron Johnson in Accumold. Thank you so much for joining us. We really appreciate it. And everybody watching, hit that subscribe. I hope that you enjoyed this deep dive on microplastics today. So subscribe, like, share, all that good stuff. And hope to see everybody next week. Have a great day.
Thanks, everyone.